Today we're going to be working with what we call the conjugate of complex numbers, and you might find this similar to what we learned back when we were dealing with radicals. When we had radicals, just kind of refresh our memory, let's say I had the number of 3 over 4 minus the square root of 5. When I have a radical in the denominator, we wanted to get rid of the radical in the denominator. And to get rid of the radical in the denominator, we introduced this concept of a conjugate. And what the conjugate was the same term that you have in the denominator, it's just that that middle sign was changed. So the conjugate of the 4 minus the square root of 5 was going to be 4 plus the square root of 5. And if I multiply the bottom by that, I'd have to multiply by the top by that. And in doing so, I'm really multiplying by 1. I haven't changed the equation at all. But what it's allowing me to do, it's allowing me to get rid of the radical sign in the denominator. Because what happens is our middle terms cancel, and then the radical signs get multiplied together, and then they cancel themselves. So an example would be, this would be 4 times 4 would be 16. I'd have 4 times the square root of 5 would be plus 4 square root of 5. I would do then the end term here, negative square root of 5 times 4, and that would give me minus 4 square root of 5. And then I'd have the negative square root of 5 times square root of 5, and that really became negative square root of 25, which we know to be 5, so it would be negative 5. These would then cancel, because it's a positive to a negative, and I'd just be left with 16 minus 5. Well, then that would just become 11. So then this would then just be 11 on the bottom. The top we'd have to multiply, and that would be like 12 times 4, or 3 times 4 should be 12, and then 3 times the square root of 5 would be plus 3 square roots of 5. And so that would be our answer. But by multiplying by this conjugate, it will just again allow the radical to disappear. Well, we're introducing the same concept today, but we're using with the complex numbers that we've just learned. We know the complex number is a plus bi, where this is the real value and that's the imaginary value. So the conjugate of a complex number in this format would be the same thing, the a and the bi, but then the middle sign has changed. So if this is positive, that's going to be negative. If this was negative, that would be positive. So it's just your middle sign. So you just want to change the middle sign. Okay? So if I look at this complex number here, 4 plus bi, and I said, well, write its conjugate. Well, it's going to be the 4 minus I, because it's the same values for a and b, but just the middle sign has changed. For a negative 2 plus 3i, for this complex number, the conjugate would be negative 2 minus 3i. Again, the same thing for a and b, just the middle sign has changed. And for 4 minus 5i, the complex number, for that complex number, the conjugate would be 4 plus 5i. So let's see how we could use this. Well, here we have an expression 3 minus 2i over negative 4 plus I, and I want to get rid of the I value in the denominator. So I want to multiply by its conjugate. So I'll just rewrite this as 3 minus 2i all over negative 4 plus I. So the conjugate of this complex number in the denominator is going to be negative 4 minus I, and whatever I do to the bottom, I have to do the top. Okay? And because I'm multiplying it, I want to then go ahead and do the distributive property. So I'll do the negative 4 to negative 4, and that equals 16. I'll do all the terms so you can see how they cancel. So I have a negative 4 to a negative I, and that will be a 2 negatives make a positive, so it's positive 4i. Here I have an I to a negative 4, so that's going to be a negative 4i. And then here I have an I to a negative I, which is a negative I squared. Okay, so looking at trying to simplify the denominator, we're going to focus just on the denominator right now, we would combine like terms. Well, I have a positive 4i and a negative 4i right here, and those are going to cancel to be 0. So I'm really just left with 16 minus I squared. Because I have an I value that has an exponent other than 1, I can actually do the substitution of those 4 i's that we mentioned. So I squared we know to be negative 1. So I could rewrite this as 16 minus a negative 1. I can substitute negative 1 for I squared. And then therefore this becomes 16 plus 1, which then becomes 17. So that's the denominator. And looking at the numerator, we go ahead and apply the distributive property. So I have a 3 times a negative 4, which is going to be negative 12. I have a 3 times a negative I, which is minus 3I. I have a negative 4 and a negative 2I, which would be a positive 8I. And then I have a negative 2I and a negative I, so the two negatives become a positive, so it's positive 2I squared. Because the I times the I become I squared. So similar to what we did below, we want to combine our like terms. So I have the negative 3I and the positive 8I, that's going to be a positive 5I. And then I'm going to have a negative 12 here. And then I have a 2I squared. Well, I squared we know to be negative 1. So this really becomes negative 2. Okay, so if we want to combine then the constants, we would combine the 12 and the negative 2, and that's going to become a negative 14. And then we would have the plus 5I. So we can't combine them anymore. So just carrying that to each one of these, that would just stay the same. So our answer appears to be negative 14 plus 5I all over 17. However, to put it in true A plus BI format, you really want to separate the denominator over the real and the imaginary. So this really should be written as negative 14, 17 is the real portion, plus 5I all over 17, and that would be the imaginary portion. So now that we've gone through this example, we'll go ahead and try this example here, the 3 minus 4I over 2 plus I. Because you have I in the denominator, we want to multiply by its conjugate. And then that should cancel out the i's. So go ahead and give that a try, and then when you're done, go ahead and come back and restart this and check your answer. If you had a chance to answer this now, then this is how hopefully it looks. 3 minus 4I over 2 plus I. I'm going to multiply by its conjugate, and that would be 2 minus I and 2 minus I. When I multiply the denominator, I'm going to get 2 times 2, which is going to be 4. My middle terms are going to cancel because I have a plus 2I and a minus 2I, and that cancels. So I look at the I and the negative I, and that is minus I squared. When I go to simplify that, I squared really is negative 1, so that becomes 4 minus a negative 1, which is really 4 plus 1. So it's 4 plus 1, which is then 5. So that's my denominator. On my numerator, I would have 3 times 2, which is going to be 6. I'd have 3, that's a 3 times 2, 3 times a negative I, which is negative 3I. I would have a negative 4I and a 2, which is negative 8I. And then I have a negative 4I and a negative I, which is negative 4I squared. When I try to combine like terms, my middle terms, negative 3I and negative AI, become negative 11I. And I have the 6 here. And then I have a minus 4I squared. Well, again, that's going to be minus 4 and then negative 1, because the I squared is really negative 1. So then this becomes 6 minus 11I plus 4, because a negative 4 times a negative 1 is a positive 4. Combining my like terms, the 6 and the 4 become, actually this is wrong, I'm sorry. It's negative 4I times a negative I, which is a positive 4I squared. My apologies. So it's positive 4I squared. So then it's a positive 4 times a negative 1. That becomes a negative 4. So it's 6 minus 4. So 6 minus 4 becomes 2 minus 11I. Okay? So hopefully I didn't lose you. Let me just reiterate that real quick. So I have a negative 4I times the negative I, which becomes a positive. So it's a negative, a positive 4I squared. The I squared is a negative, so it's 4 times a negative 1, which then becomes negative 4. 6 minus 4 is 2. So, sorry for that confusion. Alright, so now we want to put in the A plus BI format. So I would separate the 2 and the 5, which is 2 over 5, and I would have a minus 11I over 5. and then that would be my final answer. Okay, so in this portion right here, we're talking about conjugates, which is, again, the same value of a and b, except the middle sign has changed. We use those conjugates to multiply our denominators. So you want the conjugate of the denominator to multiply by 1 so we don't change the equation. The top and the bottom are multiplied by that conjugate. And then when you multiply it through, the I should cancel itself out and become a number at the bottom. If you have anything on the bottom besides a number when you do that, then you double check your math. Okay, so one thing nice about complex numbers is we're able to graph them pretty simple. On a complex plane, so the plane of complex numbers, we have a horizontal and vertical axis like we would normally have with x and y. The horizontal axis for a complex plane is, the horizontal is the real or the a value. So this horizontal, which is the left and right, okay, that represents my a, these represents my a values. The vertical axis, which is up and down, okay, represents my imaginary, which is my b value. So this axis right here, up and down, is going to be my b value. We know a complex number is made up of a plus bi. So the a value that I talk about for real is whatever the value is here. The b value that I'm talking about for the imaginary would be the value that's in front of the I, which is b. We signify that as b. So in looking at this complex number, 3 minus 2i, a would equal 3 and b would equal negative 2. I could rewrite this as a point of 3 comma negative 2. I can take my a and my b. And then I can take that and I can actually go to my plane and I can actually plot the point. So we would make the markings as we normally would. And we would treat this similar as we would to x and y, very similar to x and y and how we treat it, right? So the x is the horizontal and the y is the vertical. Well, that's how the a and b are. So I would go a, I'd go over 3, 1, 2, 3, and I'd go down 2, 1, 2. And then that would be my a point. That would be my a complex number graphed. If I look at my b complex number, my a is negative 2 and my b is 4. So I could rewrite that point as negative 2 comma 4. So this is my a, that's my b. I can go to my plane and I can graph it. So I go down 2, or over 2, sorry, over 2, and then I'm going to go up 4. 1, 2, 3, 4. And this becomes b. My b complex number is plotted there. Now if I look at c, I have a equals, well I don't see an a in front of the b value, so a is just 0, and then b equals what's in front of the I, which is 3. So if I have, well we'll get to that next. Okay, so I can rewrite this as 0 comma 3. So I could go to my graph, go to 0, that's the a value, and go up 3. And put a point there, and that is my c complex number graphed. If I go to d, my a is negative 4, and my b is negative 3. So I can rewrite the coordinate as negative 4 comma negative 3. And then I would go over my 4, and I would go down my 3. And that would be my d complex number graphed. Okay. Let's say I had e, and let's say it was just 5. Okay. So a would equal 5, and b would equal 0. So b is there, you just don't see it. At that point, I would go 1, 2, 3, 4, 5, and mark that, and then b is 0. Actually, I lied. That's wrong. 1, 2, 3, 4, 5, right here. 1, 2, 3, 4, 5, and then b is 0. Okay, so this would be e. There you go. Sorry about that. So this is going to be 0.5 comma 0. So we go over 5 and then stay 0. So that's e. Okay. All right. So now you should be able to take a complex number, find the a and b value, create a point, and with that point, plot it on a plane. Again, a is the horizontal, and b is the vertical, and you plot it very similar as you did to x and y. So now, we're just going to throw out one thing here. You can actually then go from a graph and actually then go into your complex number. And let's give you an example. Let's go here and here. Let's go over 3 on a and up 2 on b. So let's just do this, and we'll call this point F. Okay? So point F has a value of 3 and a B value of 2. Okay, so it's 1, 2, 3, 1, 2. Because I know A and because I know B, right, A and B, I can now write my complex number by using A and B. We know a complex number to be A plus BI. So if I know A to be 3 plus BI, so it's going to be 2I. So I just take my values of A and B and plug it into the A plus BI format, and I can get my complex number written out that way. So you can find it from a graph, or you can put it on a graph. Alright, and then the last concept we're learning today is what's called absolute value. If you recall, absolute value is the distance from 0. Okay? And so if I have any of these points here, and I say I want to know the absolute value of this point, what I'm really asking is what is the distance from this point here, which is 0, to that point? Or what is this distance from 0 to that point? And so this is like looking at a line from here, right? Is what we're looking at. We're trying to find this right here. Well, this actually ends up being a right triangle if you look at the hypotenuse of a right triangle. Here is the A value. Here is the B value, and then what we're trying to find is what we call the C value, right? That's the hypotenuse, the distance from here to here. So we can actually use the Pythagorean theorem to help us find the absolute value. So in showing what this would look like, let's say I take this here and bring it down, okay? I have 3 minus 2I, and I'm trying to find the absolute value. So you'll notice that you would have the absolute value lines, right? So the absolute value of 3 minus 2I equals, well, I can find it by using this Pythagorean theorem, the square root of A squared plus B squared. So A we know to be 3, and B we know to be negative 2. So therefore, I can use this equation here, the square root of 3 squared plus the square root of negative 2, or negative 2 squared. And I can then solve this. That would be the square root of 9 plus 4, which is the square root of 13. I can't solve that anymore, or simplify it anymore, so therefore the answer is negative 13. So it's telling me that the distance between this point and this point will be the square root of 13. So if I plug square root of 13 and do the calculator, it would tell me a distance, and that's from there to there. Okay? So let's look at the other examples. Let's take B. So it's going to be the square root of negative 2 plus 4I. Okay, so I'm trying to find the absolute value there. This is my B example. So A is negative 2 and B is 4. So then I could do the square root of negative 2 squared plus 4 squared. So that's going to equal the square root of 4 plus 9. 4 plus 16, 4 plus 16. That equals the square root of 20. The square root of 20 can be reduced to 2 square roots of 5. Okay? So the distance from 0 to B, this one right here, is 2 square roots of 5. Alright? Let's take C. C is going to be square root of 3I. We know A to be 0 and B to be 3. So we could do the square root of 0 squared plus 3 squared. That equals square root of 9, which then equals 3. So the distance from here to there is going to be 3. And notice how it's 1, 2, 3. Whenever you have an A or a B that is 0 and they fall on the axis, it's easy to find the distance because it's just however much over it is. Okay? And then if we look at D, that would be the absolute value of negative 4 minus 3I. So A is negative 4 and B is negative 3. That will then equal the square root of negative 4 squared plus negative 3 squared. And that equals the square root of 16 plus 9, which is the square root of 25, which is just 5. So the distance between the D value and 0 is 5. And I think in this one here I said this was the distance. Really, this is A here. So Square root of 13, this right here would be the square root of 13, this distance, because that's A. And then B, this is the distance here. That would be 2 square roots of 5. C, it's 3, so 0 to 3. And then D is going to be here. Okay, so that is using the Pythagorean theorem to find the absolute value, which is the distance from here to that point. And again, knowing A and B, we can just plug into the square root of A squared plus B squared. We're really solving then, and then that value is really what we're solving for, and that is like our quote C value. So then, just to kind of summarize everything that we've learned today, we have the complex numbers, the conjugates of that, which is the same value except for the middle sign has been changed. We then used it to multiply the congregate by it, top and bottom, so that the denominator could then cancel out to be a number. We learned about the complex plane, in which the real axis is the A going horizontally, the imaginary is the B going vertically. And that we can use those values of A and B and plot, just like we would X and Y. And that then we can use those values to find what's called the absolute value, the distance from the center point to the point, by using the square root of A squared plus B squared using the A and B values.